Okay, so the problem we're looking at today is the USACO 2020 February contest gold problem 2 of Help Yourself. You can pause the video first and look through the problem yourself. Okay, I assume you read the problem. So this problem is really straightforward. So you're given n segments, you're putting them onto a number line, and now to find the union of a set of segments to be the set of all x that are contained within at least one segment. And the complexity of a set of segments is the number of connected regions represented in this union. And now you want to compute the sum of the complexities over all 2n subsets of the given n segments, modulo 10 to the 9th plus 7, and n is at most 10 to the 5th power. And also, this problem is pretty fun. It says usually your job is to help bestie, but this time you are bestie, so there's no one to help you, help yourself. That's why the problem is named that. So you can pause the video first and think about this problem yourself. Okay, I assume you thought about the problem. So what are something that we think of when we first see this problem? Well, obviously, since n is 10 to the 5th power, you can't just find all 2 to the n subsets. And usually under conditions like this, what we want to do is for each segment, we want to see like what subset in what subset does this segment have its own region. For any segment x, we want to know for which subsets does it represent its own connected region in the union. So how can we find that? Let's say we have these segments right here. Obviously, if it's not selected with any other segments that intersect with itself, obviously is its own connected region, right? However, if it is, if we do have a region with a bunch of segments intersecting each other, then which segment do we assign this region to? Well, this is actually just arbitrary. I just said that I assign every region to the segment in this region with the leftmost left component. So this whole region will belong to this blue segment right here. So then now we can find for which segment J can we not select in order for I to be its own region. So right now we're considering the segment I, and for which segments can we not select in order for it to be its own region. So let's say we have segment I is this red segment right here. So which ones can we not select? Well, obviously the ones where they have the left segment on the left side of the left end and the right end on the right side of the left end, which means just any segment that contains the left end within, because those are the only segments that both intersect with I and have left end to the left side of the left end of I, right? However, this is not that easy to find since we have two constraints, both left on the left side of the left end and right on the right side of the left end. So an easier way to find the number of segments that satisfy this property is that for each segment, we find which ones is a blocking, like which ones can if we have, let's just consider every single segment J, and a segment J blocks I is when they cross over the left end of segment I, and we just consider how many segment I do this J block, right? And that's pretty easy to find. We just put every single left end of every single segment into an array. We sort that array, and then for every segment we meet, we binary search the first one to be greater than or equal to the left end, and the first one to be less than or equal to the right end. And every single segment with a left point within this region that we just binary searched is going to be blocked by this segment, right? So here's my implementation of that algorithm. Basically, so here we have the left end, right? We sort them. We put them in the SL, the sorted left. We sort them, and for each one we use a prefix sum difference. That's not really even an algorithm. It's just a method, prefix sum difference. You do difference. Here's the prefix sum, and then for each segment you find out which ones cannot be selected in order for this segment to be its own connected region, and we store that in the count. And each time we have to do that, we have to write a fast power ourselves, because if we just do the C++ standard way of one move left to the pow, that's not going to give us the right answer because we're not taking the remainders. So we have to write our own fast power and take the remainder each time, mod 10 to the 9th power plus 7, right? And for all those subsets, this segment I is going to be its own connected region, and we add all those up to get the answer. So basically, this problem is pretty easy, I would say, for a gold problem, even though it's significantly harder than the last one of the same contest, the problem 1 of the 2020 February gold contest. That's the timeline, and it's just topological sorting. If you haven't seen my video over that problem yet, you should probably go check it out. It's really easy. So this problem is significantly harder than that one. However, it still doesn't involve any algorithm, I would say, because prefix sum difference just a simple technique from Silver group. So even though this problem involves a lot more thinking, it's pretty easy, I would say. So hopefully after this video, you will understand how to solve this problem, and I hope this video helped. Thanks for watching.